afternoon, my YouTube viewers. It's Crystal here. In this video, what we're going to do is we're going to talk about randomized block design, which is a type of experimental design. So, in randomized block design, units are grouped into blocks based on a known characteristic, such as soil type or age. Treatments are randomized within each block to account for variability between blocks. So we've got an example that we're going to actually cover in this video. And then we're going to carry out randomized block design with this example. So we have 3 fertilizers or treatments are divided into 4 fields or blocks. So the null hypothesis is no significant difference between fertilizers or fields, and the alternate hypothesis is significant difference between fertilizers or fields. So we're going to carry out this experimental design with the randomized block design. We're going to have 1 factor and 1 blocking factor. Excuse me. So the first thing we're going to do is we're going to set our seed. And the reason why we're going to set the seed is so every time you run the program, the variables are going to be initialized to the same values. So you type set.seed brackets 1, 2, 3, and you can type any number you want within the bracket. So your tree is going to be a factor, brackets, and a replicated vector of F1, F2, F3 times F4. So that means times 4. So that means you're going to have 4 F1s, 4 F2s, and 4 F3s. So that's going to be 3 treatments times 4 blocks. And then the block is going to be a factor with a repetitive vector of B1, B2, B3, B4, and each is going to be 3 times. So there's going to be 3 B1s, 3 B2s, 3 B3s, and 3 B4s. So we're going to simulate the yields. So the treatment effect plus the block effect plus noise. So treat effect is a vector of F1 equals 15, F2 equals 18, and F3 equals 20. And the block effect is also a vector. B1 is 0, B2 is 2, B3 is -1, B4 is 1. And so your yield, it becomes the treat effect of the treat and the block effect of the block. And it's going to be a randomly sampled normal distribution with 12 samples with a standard deviation of 1.5. And then so we're going to take this and we're going to create a data frame out of it and call it DAT. So DAT becomes data.frame brackets block, comma, treat, comma, yield. So we come down here and we look at the data frame that we have created. So your block is going to be B1, B2, B3, B4, and 3 rows for each B number. And your treat is going to be F1, F2, F3. So B1 is going to be F1, B1 is going to be F2, B1 is going to be F3, and then you repeat that for B2, B3, B4, and then you have your yield, which is the sample of the randomly sampled normal distribution. So it's going to be the randomly sampled normal distribution. See if I can find it. Yeah, R norm 12 is going to be the number of samples, and the standard deviation is going to be 5. So now what we're going to do is we're going to perform an ANOVA on the randomized block design, and the ANOVA that we're going to be used is going to be for a linear regressive model. So you have two types of ANOVAs. One type of ANOVA is for a hypothesis test, and the second type of ANOVA is for a linear regression model, and we're using the ANOVA for the linear regression model. So fit becomes AOV brackets yield, and that's a tilde treat plus block. So yield is your Y variable, it's your dependent variable, and treat and block are your independent variables. And data is dat, and then we're going to make a summary of this model. So the summary of the model is degree of freedom for treat is 2, block is 3, and residuals is 6. So basically, you've got 3 samples for treat, so 3 minus 1 is 2. You've got 4 samples for block, 4 minus 1 is 3, and you've got 12 samples for residuals, and 12 minus 6 is 6. So you've got your sum of squares for your treat, your block, and residuals. You've got your mean square for your treatment, your block, and residuals. You've got your F value, and then you've got your P value. So your P value for the treat is 0.002, and your P value for your block is 0.03. So both of these P values are actually less than 0.05, which is generally the significance level. So both of these P values, you would reject the null hypothesis in favor of the alternate hypothesis. So the null hypothesis is there's no significant difference between treatments, and the alternate hypothesis is there is a significant difference between treatments. So because we've got we've got a low p-value for the treatment and a low p-value for the block, and that means there's a significant difference between the treatment and the block. So now we're going to plot the treatment means with 95% confidence interval, and we're going to compute the adjusted means. The simple group means are fine for teaching. So treat means becomes T apply, brackets, dat, $ yield, comma, dat, $ treat, comma, mean. Treat SD becomes T apply, brackets, dat, $ yield, comma, dat, $ treat, comma, SD, which is your standard deviation. N per treat becomes length, brackets, unique, brackets, dat, $ block, which is 4 blocks. And then CI lower, that's the lower confidence interval, becomes treat means minus 1.96 times treat SD divided by the square root of N per treat. And then CI upper, which is your upper confidence level, becomes treat means plus 1.96 times treat SD divided by the square root of N per treat. And then now we're going to make a bar plot out of this. So centers becomes bar plot, brackets, treat means, comma, y lim, which is the limit on your y-axis, which is a vector starting at 0 with a maximum CI upper times 1.2, and your color is a vector of steel blue, tomato, and gold. Your y lab, which is the label on your y-axis, is yield. Your main is your title, is randomized block design. Treatment means with 95% CI, that's confidence interval. Now we're going to put some error bars in there. So arrows, brackets, centers, comma, CI lower, comma, centers, comma, CI upper, comma, angle equals 90, comma, code equals 3, comma, length equals 0.08, comma, line width equals 2. So now we're going to do our ANOVA diagnostics. So PAR brackets MF row equals a vector of 1, 2, and then we're going to plot brackets fit, which equals 1. So that's residuals versus fitted. And we're going to plot brackets fit, which equals 2. That's your QQ plot for a normal distribution. And PAR brackets MF row equals a vector of 1 and 1. So we're going to look at this. So this is the randomized block design that we have created. And so you see that we've got bar plots of F1, F2, and F3. So the yield is going to be 15, 18, and 20. And if we go back and look at the data that we simulated, we say F1 equals 15, F2 equals 18, F3 equals 20. So that is the mean. That's the mean that we've created is 15, 18, and 20. And then so you've got your upper and lower 95% confidence intervals for F1, F2, and F3. And then we're going to also plot our diagnostics, which is the residuals versus fitted. And so the fitted values is a little bit wonky, but the QQ residuals, that's a little bit wonky too, so it's not really on a normal distribution. But we've already ascertained that the p-value for all F1, F2, F3, and block 1, block 2, block 3, block 4 are less than 0.05. So we've already ascertained that there is a significant difference between the treatments and the blocks. So that concludes this video. The next video is going to be on another experimental design. And so I hope that you watch the next video and that you got something out of this video. And thank you for watching.